Hello and welcome. Here we are in a lecture 11. So remember the last lecture we were talking about functional programming in quotes, but learning about things like map, for each, and zip. So notice how all of those operations were element-wise, right? Map takes an element in, applies a function for each element, and then gets another element out at the other end, right? And so there's kind of very much each element's independent and parallel. You can imagine if you had a really ambitious compiler of that kind of description, you could even do them all in parallel, right? Why not, right? And so today we're going to talk about some other types of functional programming operators that are more about aggregating things, right? More about combining and reducing. In particular, one of them actually is reduce. And so just to make sure we're all on the same page about terminology, uh, I keep saying functional programming for this stuff. Really what we're talking about technically are higher order functions. This is just one aspect of part of many functional programming languages, but detail. Okay, so, as I said, we're going to talk about aggregating things. So in this case, it's both reduce and fold. And we're going to do a few things along the way. We're going to talk about a little bit about reading these Scala type notations. So as you go read the Scala API docs, it'll be more clear. We're going to talk about something called zip with index. And then finally, we're going to go back, like we've done in the prior examples, and redo some of the models we've seen in prior lectures with these new constructs. And we'll see, when it can be done, I would arguably in a good way, and when it can be done perhaps in a not so good way. Just because it's possible doesn't mean it's necessarily the best way to do it, right? We've kind of always been talking about choosing between alternatives and what's perhaps the most readable or easiest to maintain code. And I think this kind of functional programming stuff, if done correctly, can be really, really great, but it's also really easy to abuse, and then it's very hard to deal with. Um, okay, let's go ahead and load up our notebook. Okay, we're rolling. All right, so as I said, the prior things we dealt with, they were all element-wise, and now we want to somehow collapse or aggregate things, right? And there's a few things to keep in mind. Number one, you of course need some sort of function that, takes multiple and reduces it down to one. That's going to be required. The other thing to consider is how we handle these kind of degenerate cases. Remember, with our, delay module, we had to handle that case of what if we want to delay zero? Could we handle that or not, right? Or in the case of this reduction thing, how do we reduce if there's zero things? How do we handle that gracefully? So let's talk about these ones in turn. First, let's do reduce, right? So reduce, as you see specified here, give it a binary operator, and it simply applies that linearly until you're down to one element, right? So if you have n elements, it's going to apply this thing n minus one times to get down to it. So for example, if I have a sequence just of, some handy numbers, and I call reduce, we can go ahead and reduce that down, right? So maybe I'll go ahead and even comment these out momentarily while we run this. We say, oh yes, we can add them all together. So we had this collection, add together is all 15, right? And so you can do it to function literal syntax like this, the two arguments and then being applied together, or we can use even this, wildcard replacement thing we were talking about from last time. So this is the first argument, this is the second argument. That's pretty cool, right? So we had this collection, we just called reduce on it. Likewise, often you might combine these operations together, right? So for example, we could do a map on that collection now. So now we have all the squares. We could then, we will go ahead and run that real quick so you see it, right? 0, 1, 4, 9, 16, 25 as we squared them all. We can, of course, add all those up with reduce like we just did. And, now that we're really cooking, we could do this all in one line, right? We did the map and we did the reduce. So remember, this is that, syntax in Scala where you can, use spaces rather than use spike punctuation. This is the same as, collapsing all this, right? The same thing. So cool. That's reduce. Now, one might wonder, okay, well, there's got to be a catch, right? Yeah, let's talk about some catches. But before that, let's go ahead and apply it. So remember one of our prior examples, we had this arbiter. So before we talked about functional programming, right? So we had this for loop to go out and grab stuff. We had to declare our y or vex in advance, and then we connected to on both sides. It was quite a bit of work. And then last time we improved out functional programming. We replaced those loops with maps and such. It was pretty slick. Um, one of the things you may remember was we had this case where we had all these invalids. We wanted to somehow order them all together. So we used an OR reduction. So there was a built-in feature of the language. We had this OR reduction. In order to use it, we had to cast to a UN first. Okay, so we did all that. Here we're doing the exact same operation just by calling reduce, right? So this is perhaps a more generic, more portable, more clear thing. How many people are familiar with Chisel's, reduction operators? They're pretty rarely used. Um, Here's a much more general thing, right? You can just say, hey, let's go ahead and reduce those, right? And it's the same hardware. And so the other functional programming stuff we covered last time, like map, for example, here. But yeah, so reduce, in some of these cases, we have a very clear aggregation. Really, really handy. Cool. Maybe I'll pause for any questions so far. Okay, cool. So this is the catch, right? How do I apply a binary operator to 0 elements? How do I apply a binary operator to 1 element, right? So it's not just even 0 is a problem. Even just 1 element is also a problem, right? Um, or what was a scenario where I have elements and they're all of one type, and I want to somehow aggregate them into something that's actually a different type? With reduce, that's not quite possible. And so thus we're going to need another operator, which is fold left. So maybe it's perhaps easier if I actually skip ahead the slide and go to our diagram. So then if this is a fold left, also implies this is a fold right. So that's why we have both. Let's focus on fold left. So what does fold left do? It takes in a collection, and for every element, it starts from the left. That's what leftness term refers to, is starting from the left. It takes that element and some initial element you're going to give it and applies the function to it. So the function is binary. It takes in an input from the element and an input that's given, creates something new. And that something new is then passed on into this function again, and then you combine another element, right? So every step of the way, this function is binary, and it's taking an element from your collection and its initial thing. If you don't have any elements, of course, you just get initial thing back. It doesn't even apply to function. You just get it straight to here. So you can see that, between fold left and fold right, sometimes there's a confusion language-wise of what this means. You hear fold left, that phrasing you might not know any better. It sounds like it's going to the left. However, we can see as drawn, this is very much going to the right. Now, if you put n-1 on the left side, then it is going to the left, right? So you can decide which is, maybe more clear to you. But maybe you can think of fold left as ascending in terms of indices and fold right as descending. So you can see fold right, exact same structure, it's just starting from the other end, right? Okay, so let's go back to the text for a second. Yeah, so like I said, left, in this case, is 0. And so that's why I said it's ascending, right? And so there's a few different examples here. So maybe kind of break them apart. Maybe go ahead and even comment them out momentarily. Okay, so we have our collection. To reproduce to be functionality of reduce, it's a little bit verbose, right? We need an initial element, 0. We need a binary function that takes in, the total so far and a given element from the collection, and then we have our new value, which will become the future total so far. So you can see, which is a very verbose thing of explaining all of that. And yeah, it does the same thing, right? Just adds up to 15 as expected. We perhaps could write the function a little bit, more concisely with the placeholder syntax. Sure, still 15. This is one of those cases where reduce works plenty well, right? Why not use reduce? So that's pretty clear. And then finally, as you can see, actually Scala has so many things built in. There's actually a sum operator. And what's actually kind of fun about it is actually the sum operator technically does reduce with the collection types plus operator. So if you define your own crazy type and define something that makes sense for a plus operator and associate that with it, you get this for free, right? That's kind of cool. So these collections in Scala have a lot of built-in features, and you kind of these things where it's like, oh yeah, there's these common patterns just kind of there. So sometimes you wouldn't think to expect the language to have certain features. We said read the API docs, and look at it. Occasionally, IntelliJ even suggests these to you if you aren't aware of them, but it's gonna be a little more proactive, try and find them. Cool. So with this one, so far we're just kind of doing totaling. So this is very much something we could do easily with reduce. So it's not clear why we're talking about fold left. Perhaps a better example is this next one, where we're going to try to find the max of a list, right? So we can go ahead and make a function which, given two elements, returns the max, right? So the max so far, anything you're comparing against. Uh, if the new thing's no bigger, who cares? Otherwise, turn a new one, okay. And then we can go ahead and call this on our new one, right? So hey, let's take that collection and find the max so far. We can see it was 0, right? Great, okay, that also works. And also, once again, Scala has a lot of things built in. There's a max operator built in. So, like I said, in these cases of max and sum, it exists in language. I should be aware it exists. But the reason why I have these lectures is more to talk about the examples above them about in terms of fold left and such. So far now you know kind of reduce and fold left. And you're kind of wondering, okay, when you're going to use these? We'll have some chisel examples in a minute, but maybe I'll pause for any questions so far. Okay, cool. Well, let's keep going then. So before we get too deep into this, I kind of want to cover a few syntactic points because they kind of been coming up and handling them indirectly. It's worth kind of being more intentional about that. So one of them, something we talked about very early on, and it's worth kind of being formal about, is this notion of currying, right? That is, we have multiple argument lists, right? So we have here a function that takes in two arguments, two arguments in the same argument list, or we can have a function that takes in two arguments, one per argument list. And so what's cool about this is we don't necessarily have to supply all these things all at once, right? We can supply them separately. So you can say, hey, I'm going to produce this function f, which is a partial application of this plus x function. So I've already hardwired this x to 1. So this function that remains only takes one argument for b. So it's now a unary function, right? Where it was a two-input function, we've hard-coded one of them, and now it's another function. So yeah, we can go ahead and run it, right? So you can see, for example, yeah, we add 1 plus 2, that's 3, sure. But it's the same as doing this, except, in this case, we've already bound f. And so this can be helpful, for example, is let's say I'm using a high order function like map, and I want to do it. And of course, map, of course, needs a unary function, right? It applies this function to every element in isolation. And so somehow I need to, parameterize this, right? In this case, we're parameterizing this plus x. Well, we can parameterize the x, and then it's going to add x on to whatever it's done. So now we have a function here that will add 10 onto each of these elements, right? So we can kind of do that. Questions? Yes. It acts as yeah, good question. So for each element coming out of the seek, it's the second argument, and the reason why is that this already binds the first argument. So when you provide arguments to these, curried functions, it applies left to right. So at this point, we've bound x to 1, or over here we bound x to 10. So now we have a function that remains. It still has a single argument to go, and that's going to be the one we're providing. So the reason why we're talking about this, I'll peek ahead and come back to this, is that for things like fold left or map, we actually, or especially fold left, it has two argument fields. So that's kind of why we're talking about this. So we're kind of more familiar with syntax. But let's go back. You're right, it's a little bit silly because a lot of languages, usually have a single argument field. Why break it up? The reason why you want to break it up is because you sometimes want to apply them at different times and places, right? Where I can have a more general function. Let's say I want to have a function that didn't do that. Like, or maybe a better way of saying this. Let's say I did this without breaking it apart, right? So let's say I wanted to, we'll call it plus a, right? A int, b int. So let's say I didn't have the thing above. Okay, and I tried to just toss this in down here. what's going to happen? It's going to mismatch, right? Because I have a function that takes in two arguments, and I need one that takes in one, right? That's kind of what's kind of required for a map operation. So you say, oh, well, what if I want to somehow bind A to 10? Well, how could I do that? Well, one way you could do that is you could define a function literal, and then, sorry, you're going to take in one argument, that's the detail, right? In this case, it's B technically, I guess. And then we can go ahead and say, hey, I want to put 10 in B. Okay, after that, we got there, right? So you can kind of see what's going on. If we created this function literal, this is a function that really takes only one argument, right? And we happen to be calling a function that's designed to take two arguments, and we're actually just hard coding one of those arguments. That's kind of what we can do with currying, right? We can fill one of these fills earlier on and get a function that now has that already applied. And this is kind of another level of like generating, right? In the way we are generating a function, right? Where we had the super general function by giving it this argument. It's still a function, it's just not quite as general, right? We've already hard coded one with inputs. And so sometimes it's kind of convenient where we can kind of construct functions this way. Yes. Yeah. You definitely have another parameter in there like this. Now in this case, B wouldn't be okay because it would be the same argument, same name twice. It need to be a different name. It need to be C. Yeah, it would need to be a different name. Yes, another question. Oh yeah. The currying can be done arbitrarily. I usually have only seen it done two, at most three times, but yes, you can go arbitrarily. It also sometimes syntactically becomes convenient in the language where when it comes time to specify a function, like this function literal down here, by having um, the last curried argument field be only a function literal, it makes it easier for the compiler to kind of resolve the boundaries of your function. Imagine if I had to do this and then like x comma this, right? That'd be like imagine instead of map taking a single argument, taking like two arguments, like one an argument and the other one's like a function. That'd be a little hard to differentiate. So a common pattern is there's something that's going to be a function body or something. You often leave that one separate. At least it's easier for the compiler to kind of resolve that whole condition. Yes, another question. It's an example occurring. Yes. Yeah. The test bench we use for testing, which I don't know if I have any in today's lecture, definitely example occurring where it's like test and you give it like the module instance or any arguments, and then it's also the body, right? Yeah. So this is part of why we're talking about currying today, is that the things we're calling are using currying. So you can probably get through this course just fine without ever designing your own module or function that does this intentionally. But the reason why we're talking about it is you're already using things that are doing this, right? For example, seek.fill, seek.tabulate are already taking these curried lists. Actually, that's a good example. So maybe, oh, this will be fun. Okay. Um, so we can take um, that seek.fill, which remember takes this many elements with this value. Why don't we say 3, right? So it's going to take 3 elements whatever it's given. And now that we have this, we can go ahead and chuck it into the map. And why did I blow this up? Oh, I need to give it a type. Nope, that still wasn't it. Is that gonna make it happier? No, it's not gonna make it happier. Okay, what if I just paste it inside there directly? I don't have to worry about defining a function literal. If it doesn't work, we can move on. It's okay. Uh, okay, super verbose. This will work, but it's not going to show the thing I was trying to show. Yeah, it succeeded, but it didn't show the syntax. But still, you can imagine instead of the query, you can apply the argument once and not the other time. As you saw, sometimes Scala gives you error messages and you read them and they make some sense and it's not quite what you want. You keep working on them. They're getting better. I will say 2.13 is more clear than 2.12. I was working some code as 2.12 the other day and it's like, oh yeah, I forgot. They did get better. And presumably Scala 3 will be better still, which came out a year ago. So Chisel's not Scala 3, but eventually will be and that'll be kind of fun. Cool. Okay, so the reason why we did this was to prepare ourselves for this next slide. We're going to talk more about some of this Scala type notation, right? So if you're digging around the Scala API docs, you might see stuff like this. So we know from before that for functions, right, it's input arguments, with types, arrow, return type. That's a function. And so thus, something like map, we can see uh, takes in a function of type A and returns a collection of type B. Now, if you're wondering, wait a second, which is which, uh, not shown is that this map came from the description of some collection, right? So there's some collection we were looking at the API docs, and we saw that uh, we wanted to call maps. Remember, map is a function on a collection. So maybe it's even better if I go jumping to our own course materials, right? We go read our Scala reference, go to the API. Oops, I broke the address. Let's say Scala 2.13 seek, for example. That sounds like a good place to go. Okay, for 2.13 seek, and we scroll down to map, right? We're looking at what's available to us. Yeah, here's map, right? So same thing we just saw. But it said map is a function on this collection, right? And not shown here, but up here, uh, we were saying this sequence is of type A, right? So what is A? A is a parameterized type, right? It's a generic, right? So you can give it different types of seeks. Seeks of int, seeks of string, seeks of whatever object or module you have, sure. So this by default is actually of this type A, which is some abstract type. And the function actually technically produces something of type B. Type B is not required to be different than type A. It could be the same, but it could be different, right? You could imagine, as we saw examples of map earlier, we took in a collection of Scala ints and then we mapped them all to chisel uints, right? Perfectly fair game. So yeah, so you can see these things in more detail, right? Okay, it takes in a function. Remember, it's being called on a collection already of type A, and we get a collection of type B. Okay. Fold left, meanwhile, takes in the initial thing. They call it the Z or the zero, right? That's of the type B, and you can see more clearly what fold left does. Okay, I need something of type B, in this case, the aggregation or whatever it is. Each of the elements I'm dealing with are type A, and then as a result of applying this function, I get another type B back. I'm going to apply this one by one, going to the left, so to speak, or from the left, I should say, and then you get this result, right? And so, yeah, this is kind of just giving me a quick primer on these notations you might see if you read the docs yourself. And instead, because these are generics, that generic parameterized type is put inside these square brackets. It's like a template parameter in C or whatever, or C++, I should say. Whew, okay, questions? Okay, let's keep going. Let's go ahead and play with these. So if you actually digging around in that API doc, you're going to find, wait a second, there is not just reduce and fold left. We mentioned existence of fold right. There's actually also reduce left and reduce right. It's like, wait, what? So what is going on? Well, so fold left, fold right reduce left, reduce right, those have certain operations, and the name tells you the direction it's applied, right? So if I say fold left, it's applying the way we discussed. If I say fold right, it's applying the way we discussed. Which way does fold apply it? Usually fold left, but not mandated, right? And so it's one of these opportunities where you can kind of see how much you want to clarify. Um, in the places we use reduce, we typically don't bother saying reduce left or reduce right because usually what we're doing is associative, meaning the order doesn't matter. So just reducing is good enough. And so kind of in the code, we see that usually reduce is fine because we're doing some sort of associate reduction. If we really care about the order, if you give the order, typically it'll be fold left, this kind of stuff. However, why might we use fold right? Well, sometimes you want the exact opposite order as fold left, right? So you could take your collection, call dot reverse, and then call fold left. Or instead of going dot reverse fold left, you could just do fold right. And that's what it's for. Okay, let's go ahead and try that out. So remember we built this reducer early on in the quarter. And what did it do? Well, it simply took in the vector and added them all together, right? So we showed you perhaps doing a for loop in var. You can just go ahead and add these together. The Verilog is what we expect. Okay, that adds them together, sure. Well, what if we want to do this with the functional programming, right? Higher order functions. Well, we can just reduce it. That's not too bad. Same code, very clear. We're reducing. And this term, for those who are trying to wrap their head around it, the term of reduction is a common kind of programming construct in terms of, as the name implies, given something, collapsing it down to one, right? So if you have a for loop that seems to be totaling up all the elements, that's a reduction, right? And so reduces, is an example of that in this case. Cool. So I would argue in this case, this is reduce is, pretty awesome, right? We actually probably could even do this actually. Oh, no, really? Oh, because chisel unit didn't define enough. Sometimes stuff like that actually works. The reason why is not because someone wrote the stuff for chisel, but because the chisel collections inherit from so many abstract types that empower the Scala collection, so you get a lot of stuff for free sometimes. But apparently not in that case. But anyway, so yeah, cool. So reduce in this case, yeah, seems like a pretty cool win. What about some of these other ones? Well, remember earlier we talked about doing a delay line, right? A FIFO, a pipe, whatever you want to call it, right? And so one of the ways we did it was with recursion, right? So we basically could iterate, and we just kind of kept calling ourselves till it was done. So if we want to do delay line 3 deep, that worked. Now, if you try to do this with the functional program we taught you on the last lecture, just with map, it's not really clear how you could do this. If you're really sneaky, you might be able to do it with for each and kind of have some secret mutable state. But how would we do it with the functional stuff? Well, let's try it out. So in this case, what we're going to do is we're going to do a fold left, right? So the word fold is confusing. It's more thinking about the fact that we're iterating through the space. So what are we passing through? Well, we're passing through our last connection, right? So here we kind of have this notion of last connection. That's kind of what this is. And so initially, we initialize it to io.in, right? So just like when we called our recursive function, we initialize last connection to io.in. And then our function goes through it, and for every iteration, it wraps the last connection in the register, and then passes on to the next iteration. That's kind of what this is doing, remember? So the result of this function is going to be input to the next invocation of this function, called as the next element from the collection, right? So this will give us the same result. As always before, sometimes the naming is a little different for registers, but the function topologically is the same. Cool. Questions? Okay, cool. So that's fold left. Now let's talk about zip with index. So last time we talked about zip. Occasionally there's times when you do zip and you actually wish you had numeric indices too. And so what zip with index does, as the name implies, that given a collection, it goes ahead and zips, i.e. pairs every element of that collection with its index. You have a new collection coming out of this that is the original element, comma, its index. Um, so if you've written Python, you've maybe seen the enumerate method. This is very similar. And so yeah, we can go ahead and give in this collection. You can see the operations here. For example, 5, 6, 7, 8, there's a collection. We can zip it manually with those indices, sure. Or we can call zip with index, which is what it does. Okay, now given this result, we can play around a bit. Let's say we want to maybe multiply every element by its index. Well, the result of a zip, whether it be zip by itself or zip with index, is going to be a tuple. So we're given a single tuple. We can go ahead and grab the fields out of tuple. So this is the first and second field. Remember, it starts from 1. Or we could instead pattern match on a tuple and break it up into individual variables for the fields, and then we can multiply them together. But you see the same result either way. Cool. Questions? Um, so let's go ahead and play with some of our functional code from before. All right, so remember we built a priority encoder, right? So how the priority encoder worked? There's two ways to do it. We could do it with AND gates or we could do it with muxes. Remember muxes, by taking advantage of the connection order, that kind of had the effect of having the precedence ordering. So we did that recursively. So yeah, you can see, for example, eventually we get down to 0. It's not anything available, but until then we keep chaining together these muxes, right? So we can do that exact same functionality with the high order function. Maybe first it's good for me to run this and remind us kind of how this behaves. You can see, for example, if we're given input, we want to find the lowest bit. We were defining our priority in that order. That's 1, right? So in this case, nobody's 1. In this case, it's 1. In this case, the second bit's 1. They're both 1. We want the lowest one, right? You can see, et cetera, how it works. Okay, so how might we do this with higher order functions? Well, let's go ahead and activate that. So what do we do? Well, our input is a uint, which is a single thing, right? And for this functional programming, we kind of want a collection. So we're gonna go ahead and cast that to as bools. So it's actually, maybe not as explicit as I might like, but as bools means a vec of bools, right? So now it's a collection of 1-bit signals. So now we turned our number, which is a multi-bit thing, into a collection of 1-bit numbers. So we have a collection. We can go ahead and zip them with the index, and we can go ahead and go through it. And every zip it away, we can go ahead and apply this mux. Now you may notice, oh, wait a second, I called dot reverse in here. And that's because the way we talk about fold left, it goes from 0 index up, right? Fold left. What that means, in the case of our precedence orderings, we're trying to behave, we want 0 to have the highest precedence. So it's the first mux rather than the last mux. That means it has the lowest priority, which is why we had to reverse it. So that's a little bit awkward. We can fix that. Actually, we'll go ahead and fix that first. So we can say, oh, how do I fix that? Well, we talked about that. Rather than doing reverse dot fold left, you can just call fold right. Now, the catch, and something I don't like them for in the Scala team, when you call fold right, the order of the arguments to this thing changes because now you're going the other way. So when you draw it out, so notice how you have two things and it kind of gets split over there, right? So now we got to do from the other side. So there's so far as now on the right side instead of the left side, as well as what we're given. So remember, to remind you're probably wondering, wait, what am I being given here? I'm being given a tuple? Why am I given a tuple? Well, we called zip with index. The reason why I need that index is so we could give the constant literal to make the right input to that mux. And then B, of course, is the input. Sure, that's going to control the mux, but we also want this literal. So yeah, we can call fold right like this. Personally, I call fold right so rarely. If I ever had a scenario, I'd probably just call reverse and fold left. But we can also be honest with each other about, what? Do we think this is an improvement over the recursion? Or perhaps a well done for with var? Maybe not. Worth trying it out, worth playing around with it, see how you feel, see if you can do it. But yeah, I see some eyes being a little confused, and yeah, I don't blame you, right? This is not necessarily super intuitive. It's worth looking at it a little bit, try and play with it, and see if you can learn this, because this is new to you. But yeah, That's kind of situation with that. And I remember from last time, I also want to keep reminding people of this, right? We don't need to write our own priority encoder. There's one built into the standard library, just so we're never forgetting that detail. We can always reuse. But uh, the point of fly was to play around with redoing this one thing. So the prior example we did with the reducer, yeah, that one I think was pretty clearly, sorry, the reducer, the first one, with the reduce, I would give a pretty good rating to that one. The fold left for the delay line, this one might look counterintuitive. If you do more fold left experiences, it might still seem pretty good. Um, this one I'm more mixed on, but we did it. We tried it. We're trying out new things in 2023. That's no longer January, but we could say we're trying new things for a new year, and this one maybe is a little bit not our favorite. Um, okay. Before we jump into this final example, maybe I'll pause for any questions so far. All right, so this final example is that crossbar from a couple lectures ago. We did the arbitration lecture. If you remember, we had these bundles we defined. We defined a message type and a crossbar I/O. Where we have some number of inputs and some number of outputs, and each one of these ports is a decoupled form of this message. Okay. So what we're going to show is redoing this crossbar with these higher order functions, and we're going to do it incrementally. So rather than all at once, we're going to do it incrementally. And the reason why is perhaps you can kind of appreciate when it does or doesn't make the most sense, right? So in this case, for example, we're going to go after the inner loops. So there's very often a scenario with this crossbar where we have these nested loops. So right now the code is uncommented as the original for loop code, and the code is commented as the functional programming we're considering, right? So in the original code, it's this nested loop, right? Because for every output, we need to make a connection to every input, we need to make a connection to every output, right? It's kind of the constant thing. In this case, it's for every in, for every out, and then the direction is for every out, for every in. We kind of do both ways. It can kind of be pretty tedious, right? To kind of combine all these, right? So naturally, one might look for ways to start combining this stuff, right? So in the case of let's do this first one up here, right? This inner loop is for given input. What are we doing? Well, we are going to grab the readies from every output port corresponding to the input port. That's what this one does. And then we're going to go ahead and reduce those with an OR reduce and connect that to the input. Okay. So with functional programming, we could just take all that and replace that with that. So from a line count point of view, oh man, we just slam dunked it, right? We went from, what is that, 4 to 1, 5 to 1. Let's go ahead and appreciate maybe more detail about what's the complexity here, right? So we are going to go through all the arbiters. Some of the arbiters associated with the outputs. And if every one of those, we're going to grab the corresponding ready port. Okay. And then we're going to reduce them all together. So that's actually pretty cool. So it's all there. However, if you're reading this on the page, it doesn't jump off at you or like really clear what's going on. It's not just you, right? With functional programming, it's really easy to chain things together and have 2, 3 operations per line. But sometimes it's less clear. Sometimes it's better to actually do one operation per line, kind of give a variable name each step of the way of a val, like this is this, right? So here, for example, we tell you like these are all the readies, and then we're kind of doing things with them here. Here we got to kind of spend some time parsing it. So from a code complexity reading point of view, maybe this isn't as ideal. But yes, that is one option. Okay, cool. How about this next one? This next one, we have 2 loops, right? For every output, we're talking about what we're going to do for every input. And well, what are we going to do? Well, we need to go in and make some connections. In this case, we can just do these connections by calling a for each, right? So in this case, all that matters is connections. So we want a side effect. And in terms of getting the right indices for these things, we can do that actually as zip, right? We're trying to zip together 2 collections, and so we can just zip them together and then go through it, right? So this is not unlike what we saw in the last lecture we had a demo of zip. Same thing here. Yeah, so this one I'm kind of more neutral on, right? Sometimes the flow appears more clear. We can kind of say, okay, I'm iterating through the space in this. By using a for each, it makes it clear that Yes, I'm iterating, but the point is the side effects, and the side effects are, these connections. This one I think is more of a wash. This one is a lot shorter. Is it more clear? Maybe, probably. Questions, comments on this one? I'm sorry, so line 17 does what? Yeah, so it goes through, so at this point we have a collection. So this parts this line element by element. So remember, arbs is a sequence, right? So it's a collection of things, right? So we made an arbiter for every output port. Okay, so now we are grabbing the arbiter associated with this output port, going into its I/O, specifically its infield, which if you go back a slide, the infield is a vec of this flipped, or no, the coupled message. So we're going to go into the infield. So now we have a vec from one arbiter, and we're going to zip it with the infield to this module, right? So this is the inputs to that one particular arbiter, which is a module instantiated inside this module. And we're zipping that with the inputs to this entire crossbar module. So there's two different sets of inputs, right? There's the inputs to the outer module we're in, and the inputs to the module inside we're talking about. So the two sets of inputs. They are of the same size, right? The arbiter has num-ins inputs. This crossbar has num-ins inputs. They're both, in this case, of the same length. It's just two different sets of inputs. We're zipping them in together, so we have, the arbiter input and the I/O input. And given those, we can go ahead and connect them up as such. So yeah, like I said, sometimes if you think the for loops are much more clear, not a problem. For some of these assignments, we're going to ask you to try to do things with the high order functions, but to get things practice. But I think, when you start to do your own modules, your own designs, you may see what you think is the most robust and most maintainable. Yeah, so the zip is going to return a new collection of tuples. And each of those tuples are an element from this in and from this in. So yeah, so what zip does, it takes this collection. So from here, you can kind of treat this all as one collection, right? There's a lot of dotting in here. The point is that what we're talking about as a collection is the inputs to this arbiter, right? This arbiter has a collection of inputs. That's the collection we're talking about. The other collection is the inputs to this entire module crossbar. So the two collections, and we're zipping them together, and the result of a zip is, element by element, pairing them up into tuples. And that's what we get. We get these element by element pairs of an input from the arbiter, which is this first thing, and an input from the I/O, which is this other thing. Yeah, exactly. And you can see, for example, as a result of this, right, we compare like line by line, like this line versus this line. We no longer have indices here, right? And the reason why is it's automatically grouping together the right thing, versus here we kind of were manually grabbing the right things. We were grabbing things from the arbiter we cared about, which we already grabbed over here. And then we were grabbing the input associated with IP. We kind of iterated manually through all the inputs. So we're connecting input of one side to input of the other side, right? The IP to the other side. That's what we're kind of doing. But because these two collections are the exact same size and we zip them together, we're already kind of all paired up the right way. Yes, question? Oh, yes, yes. Okay, yeah, we can definitely do that. So that's suggested by the crowd. Is there a way to use zip, not quite in this construct with a regular for loop? Yes. So we could say for case And then we would take that. This should be equivalent. Um, let's see if it agrees. Da, 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 da. It may not need case here. It might be able to resolve that tuple on its own. Maybe it does. Yeah, okay. No case in this case. So sometimes it's like, where do you need case? Where do you not need case? Um, if it's unambiguous, you don't need case. And so thinking of the language syntax, in this case, no pun intended, uh, you couldn't put a function here. Versus when we did stuff like before, we had like, the application of this on like a map, it could be functionless. That's why I need the case to differentiate it. This kind of minutia is annoying. Use an ID, let it tell you what to do. But yeah, so you're right. You could create this collection, which is the result of zipping together two collections, right? And then iterate over that. So we've already kind of created that collection. We can iterate over that with a for loop or a for each, right? It's kind of very similar. But yeah, I appreciate these what ifs because that kind of gets the point across. So yeah, so at this point, I would say for to give ourselves a scorecard, um, this first one, probably a win. Definitely a line count win, but complexity, understanding win. I would say medium. Uh, the ability to name things in between maybe can make a better job than it does like this. Um, the one advantage to having it all in one line like this is you can kind of read from right to left. Sometimes intentionally we're thinking, okay, what are we doing? Well, the whole point of this is to reduce something, and then we're going to connect that to ready. So we're connecting ready to the reduction of what's here, as opposed to here you're kind of reading it and it's like, where is this going? So sometimes reading right to left for functional programs is actually kind of a good trick. So this one I would say is probably a marginal win. What about this one over here? Well, we had this for each version first. It's a little cleaner. I wouldn't say it's a ton cleaner. I think this is reasonably clean, and you can imagine that it's also read by people who aren't necessarily Scala experts, right? So maybe it's a better one. But we're trying. We're trying. Okay. So after trying, notice this is inner loops only. These are two loops. What if we try to do both loops? Oh man. Okay. So let's go ahead and try this out. So um, we can kind of see how this plays out. So for the original one, and so we're starting in this case from the code from the prior slide, we're simplified. So remember the prior slide we had two loops. We did the inner loop with high order functions, functional programming. So now we are down to a single line for inner loop, and then the outer loop is still there. Okay, so for every input, we're doing this. Well, we could go ahead and do this again with the functional programming. Now, let's talk about which construct we might use here, right? Well, we want to iterate through this number range. So at that point, you're probably thinking, map or for each. What's the intended result? Are we saving anything? No, we're actually caring for the side effect. Okay, so at that point, you're thinking, I should be using for each. Okay, should be using for each. And then, do I need the index or not? It turns out this IP actually appears in quite a few places. Now, if it was just here, that might be pretty easy. However, because it also appears inside here, we actually are going to need to have that index. And so in order to hang on to the index, we're going to need a zip with index. So yes, that's the first one. Okay, so we did a zip with index for each. I would say we did it. I wouldn't know if I call this an improvement, but we did it, right? And then let's keep going, right? How about over here? So what can we do? Well, in the version after the changes from the last slide, we combine the inner loop into this one for each. There's still this outer for loop. same set of questions, right? Well, what are we going to do? Well, we're going to apply something where the goal is the side effects. So we're once again, we're going to be using a for each. Do we need the index? Actually, this OP does appear a few places. So yeah, we are. So once again, when we do this, we're going to take that collection, zip it with the index, and then call for each. Have a really complicated case to kind of remind us what we're doing. And it's all there. Oh man, it's got a lot going on. So is that an improvement? I'm also pretty lukewarm on it, right? And so if you're sitting here going, this is really unreadable, it's a little bit intentional. I'm not trying to make this hard, but it's just these higher order functions, when compounded, can become pretty unmanageable, right? And so this is the kind of thing where I think a lot of folks, when they learn about this, at first they don't get it, then they do get it, they get really excited about it, they apply it all over the place, and then they have a code that they can write and look at it even just 1 week later, you're like, what was I doing? What does this do? I don't know what this does. How does this work? And so part of what I'm trying to get across in this lecture is that using it in some places is definitely a benefit, but using it too much can be a little bit scary. Because yeah, what do we have going on? We have a zip with index, and a for each all on the same line. We have a zip and for each on this line, right? There's a lot of stuff. There's 5 high order functions here, right? So yeah, so I would argue this is, a case of FP gone too far. Maybe we went one step too far. So yeah, we can you kind of keep playing to kind of get a feel for what you think makes sense. Uh, we can play with it. It's kind of fun. Cool. Questions? So we can go ahead and put this together and run our test bench. And as a reminder, right, we can play for arbiters and change where we're messaging stuff. I did want to point out a few things, right? Uh, for example, what about even something as simple as like testing code? How about a for loop versus like a for each or something, right? Well, we can do a little better, right? So for example, for this last one, if you go read the API, you find you can actually just call clock.step with how many cycles you want. So that's an easy one, right? That's an easy simplification. And so why would you use this one versus the other one? Well, if you're not going to call anything between the changes to this thing, you might as well just call it all at once, right? With a bigger number there. But if you're going to, change the inputs, change the expects, and then call this, then of course you have to kind of break it up. That's an easy one. But like over here, okay, instead of doing that, I could have just as well have said, 0 until num out for each OP. I don't know if it's any better. I think the flow is more clear. So, like I said, take this all with a grain of salt. Be a little cautious or judicious at times. But yeah, it can be helpful. And if you're kind of wondering, why am I teaching all this if it's only like helpful some of the time rather than like a real obvious clear win? Number one, winning some of the time is still winning, so it's worth considering. Number two is that as you get more into this, you'll start seeing more sophisticated situations where this arises, right? Where part of the benefit of these high order functions is recognizing common patterns, right? The fact that, yes, I'm doing something element wise, right? So it's for each or map, or yes, I'm aggregating, it's a reduce, right? And so we get to that point across really clearly and start thinking about your code more in terms of these higher order patterns. It helps you get, I would argue, a better structure to your code and more awareness to what you're doing. And if you are able to occasionally, judiciously and gracefully use these higher order functions, it does make your code more easy to read. It does make the code tools more able to kind of compare them. Whew. Okay. Cool. Any questions so far around this? Yeah, I think that's kind of what we want to wrap up on is, like I said, we only want to use this when it's an improvement. Now, for the assignments, for the next couple of weeks, we're going to ask you or kind of force you to use it, but then it's going to be up to you if you think it's a benefit or not, right? So we don't want you to use something that's not going to be beneficial, but to learn it, maybe we're trying and see if you can get more familiar and get better at it, right? So, like I said, when we get things right, the nicest thing about it is you recognize there's a common pattern. Your codes are different. It matches a common pattern. By matching a common pattern, you can leverage existing code and structures. Other people can read and understand quickly. That's great. But the truth is, the pattern we had in this like prior slide wasn't quite the pattern, right? We have, Yeah, which pattern is this? Oh yes, the good old zip with index for each, zip for each pattern. Oh yes, that's like one I know really well, right? No, it's not, right? It's not a well-known pattern, right? A simple map, that is a well-known pattern, right? Like a single map on a single line, yeah, that's something that makes sense. For every element we're doing something. So instead, when you match an existing pattern, that's a good chance to reuse code and stuff. And here we have map and reduce side by side, right? They're good old buddies, right? Perhaps many of you are familiar with Google's work from now quite a few years ago, MapReduce. Um, that goes in there. As an aside, if maybe you learned MapReduce in a prior course, despite the terms map and reduce, there's a little bit of a slight misnomer in a typical high order function definition. So here when we do map, your job is to take an element, apply a unary function to it, and you get a new element, right? That's kind of the goal. When you do to reduce, you have a collection of elements and you apply this binary function and you get down to one element. If you remember the Google map reduce, you don't only produce an element from the map function, you produce an element with a key, right? So it's actually a tuple. And then when you do to reduce, it's not a reduce across everything, it's a reduce across everything that shares the same key. So it's a little bit of a slight revision to that model. People forget about that key detail when you hear about map and reduce, but that is there. And so, yeah. So going back to when we use this, like I said, if there's a common pattern we're matching and it matches well, and it can improve readability, simplify your code, use it. If it's overly used, right, as we saw, oh my gosh, how do I go in and modify this? What does this even represent? It can be overdone. So have some hesitation, some caution. And so what's kind of my rules of thumb or how would I approach this? Number one, what are the alternatives? The alternatives are often things like a for loop or recursion. If that's more clear, it's more clear. You just gave me the answer. You said it's more clear. So like go ahead and use that. There's a little bit of selectivity to it, but perhaps sometimes a good for loop can be really clear. Even though we can chain together operations like crazy, I say 2 to 3 operations per line at most. 3 is too much. I think two is already a lot. Sometimes even one's where we can name each thing. The other thing that people forget about the stuff is sometimes you start chaining together your high order functions and you're going fast and you are writing a function and your function ends up being like 2 or 3 lines. I think you're applying in your map. And people kind of get tempted to have that map be their inline. And I say, no, forget that, pull it out, declare a def for that function. It's like a 3-line function, fine, you can make a def for that, and then you can call that function with your def name. Or maybe if you really don't want to do that, maybe just fall back to for, right? Having multiple lines have a for loop, that's an extremely common pattern. No one's going to raise an eyebrow over that, right? So yeah, that's kind of all that. We have a couple more operators we're going to cover next week. That's kind of they're getting more and more esoteric, right? We covered the big ones, right? Map, reduce, those are the heavy hitters. For each, of course. Cool. Any last questions? Cool. Well, that's all. Have a weekend, folks. We'll be posting Lab 4 in a few hours, and then we'll be good.